Designing a developer-based refactoring recommender system is the primary focus of this research paper. The authors aim to identify metrics that capture developers' willingness to apply refactoring operations, ultimately supporting the broader application of refactoring in practice. Despite the benefits of refactoring in improving source code quality without compromising its external behavior, its adoption is hindered by the high costs of time, resource allocation, and effort required. To address this, the authors propose an empirical study to investigate how product and process metrics can grasp developers' motivations for refactoring. Building upon previous work, the study explores how metrics can be used to support refactoring recommendations. The expected outcome is to quantify the value of product and process metrics in understanding developers' motivations, providing a catalog of metrics for developer-based refactoring recommenders. The paper highlights the challenges of maintaining code bases in the era of computing pervasiveness, where poor design choices lead to complex and hard-to-maintain software. Code refactoring is presented as a technique to mitigate software complexity, introducing code structure changes without altering external behavior. However, developers perceive refactoring as a significant time and resource allocation cost, leading to limited resources spent on refactoring and hindering code quality. The authors argue that choosing the correct refactoring strategy is challenging and that developers need recommendations to guide their refactoring effort. This study leverages large language models, LLMs, to analyze developers' commit messages and extract code refactoring motivations. By doing so, the research aims to provide the first developer-based refactoring recommendations, effectively targeting the correct amount of refactoring effort towards the right target. This work extends previous studies, including Silva et al. 28, and Pantiucina et al. 22, by analyzing commit and pull requests, PR, analysis to identify metrics that guide refactoring recommendations. This study introduces a novel approach to understanding the motivations behind refactoring activities in open-source Java projects, expanding beyond traditional quality metrics. Established guidelines inform the study design, which involves analyzing refactoring commits to capture the entire project change history. 3 research questions guide this investigation. RQ1: do past study motivations align with those found in software project change histories? RQ2: are additional motivations driving developers' willingness to refactor? And RQ3: can product and process metrics capture the motivations driving refactoring? These questions are grounded in the notion that refactoring is driven by factors beyond quality metrics, such as external limitations and additional motivations. The study's hypotheses are defined as follows. H0: no correlation exists between considered metrics and refactoring motivations, and H1: a correlation exists between considered metrics and refactoring motivations. If H1 is accepted, the study further hypothesizes that the identified correlation can be either negative, H1.1, or positive, H1.2. The study aims to identify metrics explaining the existence of stated motivations and provide a list of metrics to monitor and guide developers for refactoring recommendations. The methodology involves collecting data from refactoring commits and analyzing it using established product and process metrics, such as those introduced by Kami et al. And Rahman and Devanbo. This approach extends the scope of metrics beyond quality metrics and static analysis warnings, as seen in previous research by Pantiucina et al. The study's findings will contribute to a deeper understanding of the motivations driving refactoring activities and inform the development of tools and techniques to support refactoring efforts in software development projects. By analyzing refactoring commits, this study provides a more comprehensive understanding of the motivations driving refactoring activities, taking into account the entire project change history. The study's results will offer insights into how to guide developers in performing refactoring and contribute to the development of tools and techniques to support refactoring efforts. This study focuses on the development of new metrics for guiding refactoring recommendations in Java projects. Utilizing a dataset from Silva et al., which includes 124 GitHub-hosted Java projects, 222 commits, and 463 identified refactorings, the research aims to understand the motivations behind these changes. To identify these motivations, large language models, LLMs, such as ChatGPT 3.5 or ChatGPT 4, will be employed, following the state-of-the-art in Mistral 7b. These models will be trained using supervised data from the dataset, leveraging a few-shot learning (FSL) paradigm. The LLMs will analyze the commit changes, commit messages, and refactoring types and motivations detailed in Tables 1 and 2 as the baseline framework for the classification approach. By fitting the LLMs with the commit change between the refactoring commit and the preceding commit, along with the message provided in both commits, the study will analyze the motivation behind each collected refactoring commit. Moreover, the research seeks to discover potential motivations behind the refactoring activity that may not have been addressed in previous research, analyzing possible deviations from the developer's provided motivations in the real code. This could lead to novel insights into the development of new metrics for refactoring recommendations in Java projects. This section of the research paper delves into the analysis of refactoring activities in software development, focusing on the motivations behind these actions. The authors present a comprehensive list of refactoring types and their corresponding motivations, as shown in Tables 1 and 2. They also discuss their approach to capturing motivation metrics in version control history, which involves collecting software metrics at the time of each refactoring activity and ranking them based on their relevance to the identified motivations. The paper begins by detailing the various refactoring types, such as extracting methods, moving classes, renaming packages, and extracting interfaces, among others. Each type is accompanied by its definition and potential motivations for performing it, such as improving readability, eliminating dependencies, or facilitating extension. In Table 2, the authors provide a detailed breakdown of the motivations derived from developers' answers regarding their refactoring activities. This table highlights the frequency of each motivation for each refactoring type, allowing for a comparison between the motivations extracted by the LLMs and those reported by developers in previous studies. The authors then outline their methodology for capturing motivation metrics in version control history, aiming to identify the software metrics that best describe the scenarios motivating refactoring activities. They plan to use feature importance measurement techniques, such as random forest or extreme gradient boost, to quantify the relevance of each metric to the identified motivations. Additionally, they intend to statistically validate the results by testing the correlation level of the software metrics toward each of the refactoring motivations and validating the hypotheses defined in the paper. Overall, this section provides a thorough examination of refactoring activities and their underlying motivations, while also detailing the author's approach to identifying and analyzing the software metrics associated with these activities. In software development projects, identifying and validating metrics to guide developer-based refactoring recommendations is crucial. This study focuses on open-source Java projects hosted on GitHub, employing a semi-supervised multi-class classification approach using large language models, such as ChatGPT and Mistral 7b, to categorize refactoring commits. The research proposes a set of product and process metrics, including cumulative number of changes, cumulative number of active developers, cumulative number of distinct developers, normalized number of lines added or removed, file ownership, and developer experience, among others. To test the normality distribution assumption of these metrics, parametric tests like Shapiro-Wilk and non-parametric tests like Kolmogorov-Smirnov are used. Pearson's R-correlation coefficient, Spearman's ρ, or Kendall's tau are employed to measure the correlation between the tested metrics and the statistical significance of the obtained statistic. Due to multiple tests being performed simultaneously, the Bonferroni post-hoc test is applied to adjust the obtained p-values for the test statistics, accounting for the multiple comparison scenario. The study acknowledges potential threats to validity, including construct validity due to the use of large language models for classification, internal validity related to the accuracy of the defined refactoring guideline metrics, and external validity as the study only considers open-source Java projects. Despite these limitations, the research aims to provide a comprehensive analysis of refactoring activities, guiding developers in making informed decisions about refactoring activities. This research paper delves into the connection between developer motivations for refactoring and established software quality metrics. The study's objective is to pinpoint a set of metrics that could guide practitioners in performing refactoring activities within their projects. It utilizes a novel methodology employing language model analysis to analyze multiple refactoring commits and their messages, validating the list of motivations driving developers to perform specific refactoring types. The paper references several related studies on software refactoring, including Alizada et al.'s interactive and dynamic search-based approach to software refactoring recommendations, which uses NSG-AI to suggest refactorings while considering developer feedback. Kurbatova et al.'s work on recommending move method refactoring through a code-to-vec-based machine learning classifier is also mentioned, as well as Pantiuchina et al.'s large-scale study on understanding why developers refactor code in open-source projects. This latter study examines the relationship between refactoring operations and product metrics. The proposed study's methodology involves validating ground truth motivations provided by developers and identifying further potential motivations using language models. It will also identify the most informative metrics for the concerning motivations, contributing to the existing body of knowledge in refactoring research. The study will then use the obtained metrics to study time-dependent estimation of refactoring proneness, providing a concept temporal refactoring recommendation to practitioners. The paper concludes by emphasizing the significance of understanding developer motivations for refactoring and the need for a comprehensive catalog of motivations supported by a broader selection of metrics from established guidelines. This study aims to provide a set of metrics directed to practitioners to guide them when performing refactoring in their projects, ultimately enhancing software quality and facilitating software evolution. This research paper presents a comprehensive list of methodologies and techniques employed in the field of computational neuroscience, providing an in-depth analysis on their applicability, limitations, and potential future developments. The paper commences by outlining the importance of computational models in understanding neural systems, highlighting the role of Hodgkin-Huxley equations as a foundation for understanding the electrical properties of neurons. It then delves into the realm of Hodgkin-Huxley equations, detailing their mathematical structure and how they are used to simulate neural activity. The authors also explore the Wilson-Cowan model, which describes the interactions between two populations of neurons, and the Wilson-Cowan model with adaptation, which incorporates adaptive properties into the neural populations. These models are crucial for understanding the dynamic behavior of neural systems, particularly in terms of synchronization and pattern formation. Furthermore, the paper discusses the significance of Hebbian learning rules and spike timing-dependent plasticity, both of which are essential for understanding synaptic plasticity and its role in neural information processing. The authors emphasize the importance of these mechanisms in shaping neural circuits and influencing behavior. In addition to these theoretical frameworks, the paper touches upon the use of computational tools such as Neuron and Genesis, which allow researchers to simulate complex neural systems and test hypotheses. These tools have been instrumental in advancing our understanding of neural function and dysfunction. The paper concludes by discussing the challenges and future directions in computational neuroscience, including the need for more realistic models, the integration of molecular and genetic data, and the development of new computational tools. The authors also highlight the importance of interdisciplinary collaboration between neuroscientists, mathematicians, and engineers to drive progress in this field. Overall, this paper provides a thorough overview of the current state of computational neuroscience, emphasizing the importance of theoretical models and computational tools in understanding neural systems. It serves as a valuable resource for researchers seeking to advance our knowledge of the brain and its functions.